Oh, hi. In the previous video, we defined what Huygens principle is, and we used this analogy of a car moving into a mud, and then this tire right here slowing down, and then this everything is considered as a point source. This is considered a point source. This. So as this tire slows down, it would generate this whole car to slow down. Thank you very much. So now we would use these principles for diffraction. Use this principle for diffraction. So, diffraction. Well, I want to say diffraction, but Young's double slit experiment. Young's double slit experiment, not diffraction. So, how would you? What's Young's double slit experiment? It's basically before you understand this, you have to know what interference is. So interference, like for example, if you have a wave, right, right, this wave would only constructively interfere with point where crest where it meets up with the crest and point where the troughs meets up. It would contractily interfere with a wave where the crest and the troughs meets up. So if you have this wave here, and then the crest meets up with this crest, and the trough meets up with this trough, these two waves constructively interfere. And then when you have another wave, do a different color. You have probably maybe the same wave, and then let's say this crest corresponds with this trough, and this trough corresponds with this crest. These waves are half a wavelength apart. These waves, if they have the same wavelength, they they are half a wavelength apart, and this is essential for the diffraction equation that we would later be doing. So let's say we have this wave. Let's say we have this wave. Say we have this wave. I'm gonna draw it in a straight line just so it could be better to understand and stuff. Say we have this wave. So, oops. So, yeah. Okay. So let's say we have this wave, and then let's say it's traveling this way, and we have this other wave that's traveling at this way. So this, let's say this is the crest of the wave, and this is the crest of the wave too. We don't actually care about if these two have the same crest. We only care about at the end. So if at the end this wave has a crest and this wave has a crest, they constructively interfere. And if at this point this wave have a trough and this wave has a trough, they also constructively interfere. Despite, let's say, if their path length difference, but they could only constructively interfere if their path length differs by one wavelength, because it's kind of obvious. If you have a wave, right, and then the end of this wave is, let's say, a trough, and then the end of this wave, another wave, is let's say a crest. Let's say a crest. These waves differ by half a wavelength, so they will obviously destructively interfere. But if you have a wave like this wave is much longer than the other wave. Like for example, it ends up with, let's say, a crest, and you have another wave much shorter, but it also ends up with a crest. if these two waves meet up, they will conductively interfere, even though they differ by this order of this path length difference. So knowing this, we could generate an equation, like knowing this and using Hewing's principle. If we have a double slit, so this is Young's double slit experiment. If you have this double slit experiment, yeah, double slit, and this is, let's say, the screen, and this is like the central maximum. Well, why is this called the central maximum? Because at this point, and then the path length difference is actually shown by m. So every time the path length difference differs by one wavelength, the it's the path length, the m would be equal 1, will equal 1. The path length, if the path length difference differs by, let's say, two wavelengths, the m would be 2. So every time m it's every time m is the path length difference differs by one whole wavelength, they constructively interfere. So you could write this: if the path length differs by a whole wavelength, they constructively interfere. If the path length differs by like 1.5 wavelength or 2.5 wavelengths, they destructively interfere, as we defined before. Like, we only care about the points of the wave that meet up and either constructively or destructively interfere. So if you have this double slit, and like waves would, this wave would probably hit here, and then this wave will probably hit here, and then these don't differ by any amount of wavelength, so m equals 0. This is why this point is called the central maximum, where m equals 0 for and it produces a bright band. So I should denote that by bar, and it denotes a bright band. So when denotes a bright band, so when they do differ by, and then the next order would probably be, the next order would probably differ by half a wavelength, and then you have this, and then you would have this black spot, and then you would have this series of black and dark spots based on the how much, what order they differ by. For example, okay, so as we always know, like for example, the equation for this path length difference also equals d sine theta. D sine theta. Why? Because if you consider the screen and the slit to be really far away, you could say that the incoming light would probably be parallel. So you could say this. So you could say that this slit here, with this screen, like the incoming light would look parallel, and then the path length difference would probably be equal to wait, I think I drew this bad. Hold on a second. So let's say you have these two slits. You have these two slits, and this is the screen. And let's say the two waves, they meet up at this point, and this d is the distance between the slits. The distance between the slits, and this is the length between the slit and the screen. And so you could write this equation: the path length difference, which is this path length difference, which determines whether these two waves will constructively or destructively interfere at this point, would be equal to this length over here. And let's say, since distances are measured through perpendicular segments, we say this is perpendicular, and the length D, which is the distance between the centers of the slits, equals is the hypotenuse. So, and then this right here is the angle between the two slits. As you know, like this this angle is approximately this angle, since angles in diffraction are measured from the central maxima, so the angle between the angle here is actually this, the angle between the central maxima and the wave itself. If you have the screen, it's like really far away from the slits, you could consider this angle is approximately this angle. So this angle is approximately this angle when the screen is really far away from the slits. So if you redraw this triangle here, you have a triangle that looks like this, where this is theta, and this is d, and this is the path length difference here. So this path length difference would equal d, and this is theta, d sine theta. Okay, so this is where the equation comes from, d sine theta. So d sine theta equals the path length difference, where m is the order, like the order of wavelength, is like the amount of whole wavelength it differs by for constructive interference. So for destructive interference, m would equal the path length difference will equal m plus a half wavelength, because this half wavelength produces this destructive interference, equals d sine theta. So since the bright spot for the central maxima, since is in the center, and then the following order is a dark spot, and then after that it's a bright spot again, and then a dark spot and a bright spot. The m, like when they say a dark band in the order, like the second second order of dark band, m is actually equal to 1, because if, let's say, this is the central maxima and this is a dark spot, right? This is the first, this is the 0th bright band, and this is the second bright band, and this is, let's say, the third bright band. But if you have a dark spot, this is the first dark spot. So since the bright band starts from 0 and then dark spot starts from 1, when they say to the second order dark spot, m is actually equal to 1, because m doesn't start from, like, because at this point m equals 0, and this is the first order dark spot, and m equals 0, and this is the second order dark spot, and m equals 1. I think that's kind of confusing, because at this point the path length difference only differs by one wavelength, only differs by a half a wavelength. So this whole number doesn't exist, because at this point after the central maxima, which is the bright band, the two waves at this point only differ by a half a wavelength, and they destructively interfere, because before they could differ by 1 and 1/2 a wavelength, they must differ by a half a wavelength first, because here the central maximum before, they don't differ by any wavelength. That's why they completely constructively interfere. But here at this point they differ by only a half a wavelength, and then after that they differ by 1 and 1/2 a wavelength. After that, uh, two and 2.5 a wavelength. So m equals 0 at the first 1/2 wavelength they differ by, which is the first order dark band, which m equals 0, and the second order dark band m equals 1. That's kind of confusing, but this really tricks you on problem. On the next video, I'll show you a sample problem. I know this video was kind of long and kind of confusing. If you have any questions, you might ask me.